All right. The last week of stuff before spring break / the test. Yeah. And then after that, we really only have 2 weeks of things. So that's exciting. So this is our last week with magnetism. So this coming test, we will probably need this entire week to finish up magnetism, so unfortunately we won't be able to start reviewing. But I will do my darndest on Thursday to just kind of do a recap of, hey, here are the things to be thinking about over spring break if you want to be. If you want to be, like, I get it, spring break it's got the word break in it. But I'll do a quick kind of mention of it now. So circuits. So we got 4 weeks of stuff since the last test. Circuits was one of them, series and parallel, resistors in series, resistors in parallel, capacitors in series, capacitors in parallel. Remember, if you have a bunch of them together, you need to know how to combine them into one and then work your way kind of back. That's a thing. How do you identify which ones are in series, which ones are in parallel? That is a skill you'll need. Then 2 weeks ago, we did forces on moving charges due to magnetic fields. So that was a thing, remembering that moving charges in a magnetic field experience a force. That's right-hand rule number 1. Moving charges experience a force. That force is perpendicular to the direction of motion in the direction of the magnetic field. We then expanded that to current-carrying wires. Those are moving charges. So moving charges experience a force. Right-hand rule is for positive charges. Right-hand rule number 1 is for current. If you want to find out a negative charge, it was the opposite direction. So that was all we did there. Last week, we talked about what makes a magnetic field. How do you make a magnetic field? The first case was a permanent magnet. Magnetic field lines point away from the north end, and they point into the south end. That's going to come up today. We're going to need that information for today. And then we also learned that current-carrying wires make magnetic fields. If you have a straight wire, we have an equation for that, mu naught I over 2 pi r. We use right-hand rule number 2 to find the direction of a magnetic field. Right-hand rule number 2 for the direction of a magnetic field. If you take that wire and you make it into a loop, that also makes a magnetic field. The equation for that is mu naught I over 2r. All of these will be on the formula sheet. You can, again, the formula sheet's posted, so you can kind of look through and see what's there, what's not. Also, if this is helpful to you all, I've got my note cards here. If you want to grab one, like when class ends or now, I don't really care. These will be up here. Remember, you do get a 5x8 note card on test 2. You can start working on that whenever you want. Clowy. Test 2. So everything I'm mentioning is what test 2. Test 2 will not have things on it from test 1 outside of, like, you need to know what a charge is, you need to know what velocity is, stuff like that. But test 2 has nothing to do with electric fields or stuff like that. So test 2 is just this week and the last 3 weeks. The final will be everything. The final will be everything. After test 2, we're going to cover light. So we'll have 2 weeks or so of covering light, and then we got some good kind of buffer days, review days, that kind of thing before the final. So light isn't too bad. A few rules here and there, nothing crazy. Purposefully pretty simple to kind of end the year on a smooth note. But also teach you all some things about light, which are, if you're doing the MCAT, they'll show up on there. But also if you're in the health field, it'll help you understand how an eyeball works. It'll also just help you understand what light is, and it's more, anyway, we'll get to that. All right, so today, the last things we're doing on magnetic field. So we've talked about forces on moving charges due to a magnetic field. So moving charges experience a force. We then talked about what makes a magnetic field. So force due to magnetic field, how do you make a magnetic field? Today is going to be the connection between magnetic fields and electric fields. We're going to bridge the gap between them and show that if you have a changing magnetic field, it causes an electric field. And the big takeaway from today is this is how you generate electricity. So, but this last one is the connection between magnetic fields and electric fields. Specifically, in our equations, we're going to see electric fields and voltage. That if you have a changing, magnetic field, if you have a changing magnetic field, we're going to learn that it makes a voltage. And if you have voltage, you make current. And that is electricity. So, anywho, yeah. Magnetic fields, flux. If you all remember way back, I had to do stuff with electric flux. And I told you we are covering electric flux, not because you're actually going to use electric flux, but because I wanted you to see it, because down the road, we're going to use flux again, and it will be important. And that's today. So we're going to have magnetic flux, and it is going to be critical that we understand it, hopefully because we've mentioned it before. That's going to kind of ease the transition. If it didn't make sense at all, then that's fine. But the reason I did that was for today. The main reason I talk about electric flux with you all is for that reason. Area vectors, and then, forces due to magnetic fields, and as I mentioned, voltage. So, all the things, what magnetic flux is, what EMF is, it's going to be voltage. And we're going to learn how to calculate things. Feel free to look through these, but this, what I mentioned before, I think is a good thing. So why do we care? Because the stuff I'm teaching you today is how we generate electricity. If you think about how electricity is made, batteries, like everyone's cool with that, but when you plug stuff into a wall, it's not a big battery at the end. You're like, well, it goes through a wire. At the end of that wire, though, is not a giant battery. Not yet. Maybe one day. Maybe one day we'll be better at battery storage, and that's a whole other thing. But it is a power plant. And how does that power plant run? It's got generators. It's got turbines. How do those turbines work? They spin. Okay, how does that help us? We're going to learn today. Most people know that generators cause stuff to spin. Literally, just think of a windmill. It spins. Hydroelectric dam, water goes through something, it makes it spin. Electric power plants, like a coal power plant, it heats up water, which makes the water into steam. The steam goes through a turbine. What does that turbine do? It spins. Almost all electricity, even a nuclear power plant. How does a nuclear power plant work? You have some radioactive stuff. What does that radioactive stuff do? It heats up water. The water turns to steam. That steam spins a turbine. A coal power plant and a nuclear power plant are exactly the same, except for how they heat up water. After they heat up the water, it's identical. Nuclear power plants just heat it up through radioactivity. Coal power plants heat up water. Natural gas power plants heat up water by burning stuff. But at the end of the day, you spin something. And the question is, why does spinning something make electricity? That's what you'll learn. Whether or not you need to know that in life, probably not. You don't need to know that. But it is so commonplace, and no one knows how these things work. Like, even your generator, if you're, we're in Florida, hurricane, power goes out, you have a generator. What does a generator do? You put gas in it, the gas burns, it spins something. Everything. The only case of power generation I can think of that doesn't spin something is a solar, and that's a whole different side that you don't need to worry about. I won't get into that. So, flux. If I have an electric field pointing upwards with a magnitude of 8 newtons per coulomb, what is the electric flux through a plane, which is 2 meters by 3 meters? The plane is parallel with the XY plane. So I will draw this picture for you all, and then I'll ship it to you to answer. So here's my plane. Let's say this side is 2 meters. This side is 3 meters. And then I've got an electric field pointing up. What is the flux through this? If you don't remember how to calculate flux, just guess. The whole purpose of this question is just to kind of bring it back into your mind. Flux. It is a weird thing. I'll explain it again. It's conceptually pretty simple, but for some people it kind of lands really easy. For some people it doesn't. But conceptually it's not bad. In fact, I'll tell you what conceptually it is now. It is how many lines go through a surface. How many of these arrows go through a surface? Now the question is for you to remember, how do you calculate that? Flux is just how much of this goes through it. So you almost think of like this electric field like a wind, like air. How much of this air goes through my loop? It's not actually moving, but it kind of helps to understand it. All right, interesting. People are kind of between two answers. We'll go to 140. Yeah, about 20 more seconds. We'll close this out in 5, 4, 3, 2, 1. All right, so basically it's, do we remember the equation? And I didn't expect you to have the equation memorized. But if we remember what flux is, conceptually it's how much of these arrows go through it. So the first question is, like, how do we build the equation? This is the way I kind of remember it. Well, the number of arrows is just the electric field, how big it is. The bigger the electric field, the more arrows of it, the more of it I have. The more electric field arrows. The next thing is how much goes through this thing. The bigger that surface is, the more go through it. So how do I measure how big my surface is? The area. And then the last thing we need to remember, again, think of it almost like think of these arrows almost like wind. They're not actually moving, but you can kind of like imagine these things going through this. Imagine I took this loop and I rotated it 90 degrees. If I rotated this loop 90 degrees, no arrows can go, like if I'm saying how much wind goes through this thing, nothing. As I rotate it flat, I get a lot of arrows going through it. Imagine like blowing a balloon, like blowing a bubble. If you put the thing in the right direction, you get a lot of air pushes through it, blows up your bubble. If you turn it 90 degrees, no air goes through it. So long story short, there was this thing, the angle. And the angle was between the area vector and the electric field vector. Again, this is all kind of throwbacks. The area vector, how do you get it? It's where you take your pencil and you just put the eraser on your surface. So the area vector, for example, this table in the front, just pencil on the surface, it's pointing straight up. If I wanted the area vector of my screen, just put the eraser on it, points away from it. So in this case, the area vector is this way. The angle between them is 0. So in this case, if we just start plugging in things, so in this problem, the electric field was 8. The area was 2 times 3, it's just a rectangle. And the angle here was 0. Because they were exactly lined up with each other. I had the maximum amount of arrows going through this thing. They're lined up with each other. You plug that all in, and you get 48. And you look at these units, and you're like, what the heck are these units? They come from the math. What's the unit for electric field? Newtons per coulomb. What's the unit for area? Meters squared. If you multiply the units together, you get the units that I got down here. So the units look all crazy. But there you go, flux. That's how you calculate it. Conceptually, it's how much of the field goes through the area. How much of that, how many of these arrows go through it. So that's electric flux. Great news. Magnetic flux is the exact same thing, just everywhere you're seeing E, replace it with a B. There it is. It's the exact same thing. B, so the magnetic flux, in fact, let's just change this to a B, so that what I said is correct. Magnetic flux is B times the area times cosine theta. Exact same equation. Exact same equation. You just replace E's with B's. It's the amount of magnetic field lines through that surface. Yeah, and when I say surface here, we're going to get to kind of clarify what I mean by that. Well, I'll actually say it right here. This thing does not need to be like a sheet of paper where it's like solid. In fact, we don't want it to be solid. We need an enclosed kind of thing. How do you make an enclosed thing? Take a wire, loop it. You made a thing that, again, like wind can go, that stuff can go through. You just need a closed thing. In this case, it's going to be a wire that makes a loop, or a square loop. It doesn't matter what the shape of it is. What matters? So, here you go. Bam. It's closed. That's good. I can find the flux through that. If it's like this, doesn't work. It's got to be closed. It's got to be closed. Because if I asked you what the area of that shape is, it's infinite. Yeah, it's everything. There's no... You can only have an area if I close it. So, I'm not going to give you weird shapes. I'll give you circles or I'll give you squares. That's it. Really simple shapes. Okay. The units, again, literally come from the math. What's the unit for magnetic field? Tesla. What's the unit for area? Meters squared. What's the unit for flux? Tesla times meters squared. It technically has its own fancy unit called a Weber. I will not use Weber because I have never heard someone use Weber. In fact, even these other ones. Flux is a made-up thing, but it ends up being very useful. It's a math thing. You can't see flux. You can't see magnetic field. Magnetic fields are made up, so anything following that is also going to be made up. You can't see any of this stuff. You can only see the effects of it. But it's a handy little math thing that ends up doing some cool stuff for us. But this flux concept is very important for this. Very, very important. For now, just trust me that's important. I can't explain why until we get to the why. But knowing what flux is, that it's how many of these fields pass through a thing, is very, very, very important. And conceptually, kind of understanding, I wish I had more wires. I should have brought rope or something. Maybe. Yay. All right. Understanding. So say I have a magnetic field that's going from the left side of the room to the right side of the room. If I put this loop like this, I get a lot of magnetic field through that. Again, imagine it like wind. Imagine like I'm trying to blow a bubble. I get a lot of field lines through this. This is the maximum flux. What happens to my flux as I rotate this thing? Less and less and less and less, and now I have no flux. But there's a line, again, if I have magnetic field left to right, maximum flux as I rotate this, I get less. Notice I use the word rotate. Connects to generators. Start to see As I rotate this thing, I change the flux. It goes to 0, and then when I rotate it, it increases, and then decreases, and increases, and decreases, and increases, and decreases. And we're going to learn today, when it increases and decreases, and decreases, today you just invented alternating current. We're going to see that connection. But that's kind of the punchline. A changing flux makes a changing current. Whatever. All right. If you have a magnetic field pointing upwards with a magnitude of 8t. Oh, I don't want to be mean here. This is mean. Okay. Let me double, triple, quadruple check that my answer before I even post this. I was kind of mean here and gave you an angle. And I didn't give the angle in a way that I like. So I'm going to double, triple check something before I post this for you to answer. Yeah, okay, there's both answers here. Let me be nicer to you all and say the magnetic field is at an angle of 30 degrees with respect to the area vector. And in fact, I'm going to get rid of that with respect because that just sounds fancy. The magnetic field is an angle of 30 degrees to the area vector. All right. Go for it. So it's the same problem as before, except now instead of electric field, I have a magnetic field. My loop is the same, but my magnetic field is at an angle of 30 degrees to the area vector. So I'll draw the sweet picture. So that's my loop. My magnetic field is at an angle with respect to the area vector. Here's my area vector, points directly away from the surface. This is 30 degrees. What is the magnetic flux? So again, just kind of practicing using that equation. That's the whole point of this problem. No tricks here. I will tell you if I left it as I had before. Let me think through this before I commit. If I left it as I had before, the answer would be the same. You don't need to know that. I don't need you all to be able to do geometry to kind of answer this. It's a step beyond what we need, but it's not worth the time or energy. All right, we'll go 20 more seconds. We'll go to 55. Yeah, we'll go all the way 2 minutes. All right, close this out in 5, 4, 3, 2, 1. All right, so same equation as electric flux. So magnetic flux equals B A cosine theta. The B was fairly straightforward. That's 8 Tesla. I'm not going to actually put the unit there. Just put 8. 8 times the area, which is again 2 times 3. And the question was, this angle, do I use 30 degrees or 60 degrees? That's really the question. I made it easy for you all. The angle is the angle between the magnetic field and between the area vector, which is 30 degrees. You plug all that in and you get 41.57. Make certain your calculator's in degrees mode. They kind of default to radians mode, so if you got a really weird answer that didn't match any of those, that's probably why. Just something to always keep in mind. And if we look at these answers, so if you remember last time the answer was 48, when it was dead on, I've only angled this thing slightly. 30 degrees is only a little bit. We're not even quite halfway. So my magnetic field is only a little bit lower than what it would be when it was at its maximum. As that angle gets bigger and bigger and bigger, that number will go to 0. As that angle gets to 90 degrees, cosine of 90 is 0. So when it gets perpendicular, we end up there. All right, fantastic. Let's see, have I actually, boom, and, yeah, I didn't pick that up, I was afraid of that. Boom, all right. Okay. This is a good review. And you may be like, why is this here? 1, it's a good review. 2, some of the things that we're going to use in this, we're actually going to use. Half of the skills for this problem, you're going to need for what we're doing today. This is why circuits and magnetic fields kind of went together. As weird as that seems. Again, circuits, magnetic fields, electric fields, at no point have they probably seemed similar, but we're going to see today the intersection of these two, why they're coupled together. So I have a 9-volt battery, and I have 3 resistors. And how mean of a problem this was. A little mean. This one spent some time on. I am asking for the current on this path right here. Before the junctions. Before the junctions. I am asking for the current on path 1, 2. Before the junction, before it splits into all 3 resistors. give you all some time to actually solve this. Because there is a couple steps here. There is exactly 2 steps. You need to solve for something first and then use that to find the thing you want. And this is where I told you half of this. The first step, not really going to show up in this magnetic field stuff. The second step, oh yeah, we're going to need to remember that. We'll probably go like all the way to, let's see where we're at 250. See if we need to go a little bit longer or not. But yeah, if you're looking at this and like what is going on here? Is this series, is this parallel? That's a great indication to start looking over these things before the second test. All right. I'll go to 3 minutes and then we'll call it good there. So we will close this out in 5, 4, 3, 2, 1. Okay, so we're going to talk about how you set up this problem first, and then we'll actually do it. So if you're trying to find the current here, we can't use any one of these resistors because the current splits here, and then it splits here, and it splits here. So afterwards, it gets all messy. So how do we simplify this problem? If you have a bunch of resistors, you're going to combine them into a single resistor. So that's the first idea. We're going to take this circuit, and we're going to take it and build it into one big old resistor. And then we're going to remember, so we're trying to find the current here. When we get it into one resistor, the current here is the same as the current everywhere in the circuit. If there's only one loop, remember it's like a river. Current is constant in series. Current is constant if it only has one path to take. Current only changes when the road splits, when there's a junction. When a river splits, some water goes some way, some water goes another way. As long as there's no split in the river, who cares if the river gets wide or thin? The same amount of water has to go through it. That's what current is. So, we're going to find this resistor, and then if we know this voltage, we will know this voltage, and if you know that voltage, V equals IR. Anyway, so first step, are these in series or parallel? They're in parallel. Parallel resistors are the gross ones. That's the one where you got to do. So R net in parallel, and I'll write it 1 over R1 plus 1 over, actually, I got to fix something real quick. 1 over R net equals 1 over R1 plus 1 over R2 plus 1 over R3 plus however many you have. I think I may have mentioned this to you all before. I go ahead and simplify this from the get-go. What I do is I recognize, oh, I want R net, it's on the bottom. So I put R net here, and I do 1 over all the crap. And that's what flips it to the top. And that's how I plug it in my calculator, just because the less times you plug it in, the better. You got to make sure you have those parentheses. So if you do that, you do need to convert these. They're in kilo ohms. You have to convert them into regular ohms. So R net equals, I'm going to give myself a little bit more space, 1 over 10E3 plus 1 over 2E3 plus 1 over 1E3, and that spits out 0.625 E3. In fact, let's just say 625. To be honest, well, I won't confuse people. All right, 625. Awesome. We got the resistance. Yay! We know the voltage. The last step is the easiest step. V equals IR. So 9 equals I times 625. You solve for I, and you get I is 1.4 e to the minus 2, or 0.0144. Okay. So it's like, why are we doing this? We were just talking about flux, and it seems like we took a really hard right turn to a place that, like, how does this have anything to do with flux? It doesn't. Yet. But what I wanted to make certain, one, I wanted to make certain you all remember, this is just a good reminder, it's been 3 weeks, this is going to be on the test, yada yada. But this second part is the part that I think is going to be the connection. Why does current flow? Why does any current happen at all in this circuit? It's not the resistor. The resistor is not the reason for current. This table has resistance to it. You have resistance to it. That does not mean that electricity is flowing inside that table. Everything has a resistance. What makes the current flow? It's the voltage. If you don't have a battery, and this is something you do, like everyone knows, if you don't have a battery, if you don't have a voltage, nothing's going to happen. A voltage difference, remember voltage is the same as potential difference. A difference in potential, a difference in voltage. Remember that whole ski slope analogy. One end is high, one end is low. That's what makes current flow. And we needed to remember that because I'm about to tell you that a changing magnetic flux makes a voltage. And if it makes a voltage, it makes a current. Ta-da! Moving charges, electricity. So, here's Faraday's law. Discovered experimentally by Faraday, hence why it's called after him, and someone else discovered it later. This is just kind of fun history facts. I didn't remember this. Like, my memory stinks, but it's written here and it's interesting. So Faraday discovered in 1831. Joseph Henry, literally the next year, completely independent, had no idea Faraday discovered this. He discovered it on his own. But because Faraday discovered it a year before, he gets it named after him. Ain't that how it goes? I mean, it's... Christopher Columbus isn't the best example. But, you know, there's all sorts of complications there. The first person to discover something is the famous person. At least the first person noted in history is the person to discover it. I guess we could add that on. Many things were discovered by other people before it was officially published or well known. It's the first person not only to discover something, but to communicate it to those that write history. I guess is the best way of putting it. If you discover the cure for cancer and you don't tell anyone, no one's going to name anything after you. So, Faraday won. They call this getting scooped in academia. It sucks. You could have two people working on a project. They have no idea that they're both working on the same thing. One person discovers it first. They publish first. The other people spent years and tons of money, and they call it getting scooped because they're like, oh, I don't know why it's called that, but it sucks. Imagine spending forever on something and someone else doing it. I mean, you're excited for them, but then you're also like, why? Sucks. Anywho, here's the equation. Voltage, so this E, this epsilon, it's called EMF, electromagnetic force. I am telling you what it's called. In your mind, I want you to call it voltage. It's voltage. This is technically the symbol that we use for it because it's weird. And I'll kind of make mentions to why it's weird, but as far as you all care, it's voltage. If you have a changing magnetic flux, the flux is changing with time. That thing is spinning, and it gets more arrows, and then less arrows, and more arrows, and less arrows. It makes a voltage. Now, this is equal to the negative. The voltage is equal to the negative of that, meaning as the EMF goes up, we get a voltage one way. As it goes down, we get a voltage the other way. We don't technically have a right... You're going to have to use right-hand rule. Don't worry, it's not a new one. It's one of the ones we currently know. But this negative sign is the direction current will flow. And we'll see that in a second. For now, just know that that's why it's there. It's voltage. If you have a changing, the faster this flux changes, the more voltage you make. The faster you spin a generator, the more voltage you make. Among other things. So, Anyway, changing flux with respect to time, and this is what 3/4 of this PowerPoint is just using this equation and working through it and talking about examples and trying to make sense of this. So, again, that whole wire situation. As this wire, so this is only one way to change the flux, is rotating a wire. One way, if I take this wire and have a magnetic field pointed left to right, as I rotate it, I go from a lot of flux, my flux gets smaller. I am making a voltage. And then as I keep rotating, it gets bigger. I'm making a voltage in the other direction. And now it's maximum, and then I'm making less voltage, and it's in the other direction. And then I'm making more, and it's the other direction. And it keeps flip-flopping. We're going to see some examples of that. But everything today, at least for today, we're really just going to be sitting in this equation. That's one way of doing it. The other way is flipping the magnet. Instead of spinning the coil, you can spin a magnet. North end of a magnet, magnetic field goes one way. South end of a magnet, magnetic field goes the other way. You can almost think of it like the wind changing direction. The magnetic field goes this way, and then it's going this way, and then it's going this way, and then it's going this way. Left, right, whatever it may be. A little bit more complex looking than that. So you can spin the magnet instead. That's another way. Another way is you can move a magnet closer to it. The magnetic field gets stronger the closer you are to a magnet. You move a magnet the other way, the magnetic field gets weaker. And that's basically the vast majority of the scenarios. Rotate the loop, rotate a magnet, bring a magnet close, move a magnet farther away. We'll go through all of them. It'll be fun. All right. So there you go, y'all. Okay, there's technically one other way that no one's going to do. So I want y'all to think about it. The equation for flux. What are the three things we can change? What are the three things we can change in the equation for flux? It's literally the three variables in it. So the equation for flux is B, A, cosine theta. So what are the three variables we can change? B, A, and theta. You can change how strong the field is, bring a magnet closer, move a magnet away. That's one way. Or move the loop closer, move the magnet away. We can change the area. This is the one that's a little silly. You could shrink the loop and you could stretch the loop out. Functionally, I don't know how you would do that practically. That's the most unrealistic one, but it's possible. It works. And you can change the angle, spin it. Either spin the loop or spin the magnet. Either one does the same thing. The last one is the one that actually happens in generators. It's the easiest one to do. It's pretty easy to spin stuff. Moving stuff back and forth is not necessarily easy. All right, so this is kind of the simplest case. Doesn't say why it's changing, it just says it is. What is the induced EMF, i.e. voltage? Anytime you all see the word EMF, it's voltage. I have to teach it to you all as EMF because that's what you're going to be, if you do MCAT, stuff like that, that is what it's called. That's what the equation has. There is a conceptual reason for that. It's a little tricky to explain. Voltage, you have a place that's a high voltage, you have a place that's a low voltage. So, I'll just very, very, very briefly, why do we call it EMF and not voltage? Imagine I had a loop, and I say it had a voltage, an EMF of 9 volts. So in a circuit, remember, a voltage means one part's 9, one part's 0. Anytime you hear the word voltage, a battery, anything like that, it's a difference. It's a difference. One side is, so let's, do the easier case. A battery with a resistor. This end is 9, this end is 0. Why do we use EMF? When you have a loop, what part's 9 and what part's 0? Is this part 9? Is this part 0? If so, current would go this way and this way, and that it doesn't go both directions. It goes one direction. So we use EMF because voltage isn't accurate enough to kind of explain what's going on here. At no part is it 9 and at no part is it 0. Basically, this loop experiences as if there was a voltage of 9. As if every point in that was seeing a potential difference of 9. It's not, but it's as if it is. It's conceptually weird. You don't need to understand all that, but that is the reason why. There is a reason why we don't just say voltage. But for your all's case, the reality is just call it voltage. Okay. What does it induce? Voltage. In a circular loop of wire with radius 2 meters, if its area vector is parallel to a magnetic field, which changes from 4 microtesla to 2 microtesla in 5 milliseconds. So what's given? We have radius. We have an initial magnetic field. That is not T. That should be a B. We have an initial magnetic field. That is the 4 microtesla, which equals 4 e to the minus 6 Tesla. We do need to convert that unit. We know the final magnetic field is 2 microtesla equals 2 e to the minus 6 Tesla. And our time is 5 milliseconds. Have to convert that too. All right. Okay, what are we solving for? We are solving for the induced EMF. We will use the symbol for EMF. It's just voltage, but that's the one you're going to see on the formula sheet, so that's the one we're going to write down. Makes it easier to find it. What's the equation? It's the one I just gave you. EMF equals the change, I'll use a symbol you are familiar with, change in magnetic flux over change in time. So that's the change in BA cosine theta over change in time. Okay. Now, I will not be mean in that I will only be, whenever I have you all do this, only one variable will be changing. Either B will be changing, either the area will be changing, or the angle will be changing. I will never change more than one at a time. Why? Because then you'd have to know calculus. So, to that end, if you ever have this change thing going on, you pull out the stuff that's not changing. Area is not changing, so I can pull it out. My angle is not changing, so I can pull it out. And I am left with the change in magnetic field over the change in time. Only one variable will be changing. In this case, it's the magnetic field. Now, I did forget a negative sign somewhere along the way. We'll check that in front. I will tell you all, this negative sign right now is not going to really matter. Like, it's going to, we'll put it in there, we'll plug in the answers, yada, yada. Whether or not a voltage is positive or negative does not tell you really anything at all. What's going to tell you stuff is a picture. So, we'll see it when we get there. But for now, don't stress this negative too much. I'm not going to use it to trick you at any point. You don't need to worry, is the voltage positive? Is it negative? For these problems, it doesn't matter. Don't care. Positive and negative voltage mean the same thing, as far as you all are concerned. All right. So, the area vector is parallel, so we'll just chuck that given here. The angle is 0. So now we're just going to plug in numbers. Epsilon, EMF, equals negative the area that is pi r squared. So pi times 2 squared. Area of a circle, circular loop, A equals pi r squared. Cosine of 0, that's just going to be 1. Not very interesting. And then we have our final minus initial. This will get rid of the negative sign for us, but again, at the end of the day, we don't really care about the negative sign anyway. Divided by 5e minus 3. Cool. And I don't know if I need to put parentheses around that. I'll put it around the top. All right, just plug that in the calculator. Oh, I did the ghost thing. I realized why the ghost thing happens. If my finger accidentally hits the scroll thing on the side as I'm writing, it hates it. So I do my best to avoid hitting it, but the way I write is not conducive. So I will save this, reopen it. In fact, go ahead and plug that in your calculator. while I save this thing because it's gonna chug a little bit. My computer's feeling it today. So yeah, try it out, see if you can get the answer. Be careful with your parentheses. You should get positive 0.005, and I'm not going to tell you the units, so I'll let you think about what the units are. What are the units for EMF? All right, so it equals .005. Remember I told you all EMF is effectively voltage. There you go. It is not much voltage. That is a very short period of time. But the magnetic field here is not changing that much. And this just goes to show you, so like 5 milliseconds, that's 5/1000ths of a second. That's really short. So this thing did change pretty quick. And so it kind of shows you, it's hard to make a high voltage. It requires more, a little bit more than just changing the magnetic field quickly. We have to do some clever design. The clever design is going to be really straightforward. I'll show you what I mean. I don't know if it's on the next one or what or not. Do we want to spend the time on this? I'm going to open it. I'm just going to work through it. Normally I'd give you all the time to, sure, we'll go a minute and a half, then I'll just start working through it while it's still open. So, a circular loop of wire has radius shrink from 3 meters to 1.5 meters over 5 seconds. The area vector stays parallel with a magnetic field of a magnitude 4 microtesla. What is the induced EMF? So, magnetic flux, we're going to end up solving for that. Nope, not magnetic flux. EMF equals negative change in flux over change in time equals negative change in B, A, cosine theta. And basically your question is what's changing and how would you represent that in this equation. So I'll give you all a little bit of time, then I will start working through it. I'll have the answer up here. You can pick the right answer when I do that. This is a little bit more involved than my usual ones, but unfortunately there's not really a simple way to simplify these. Notice that all the answers are positive. Again, I will not give you one with a negative voltage. Because at this point, it's not really meaningful. So I'll start just kind of chugging through this. People are split between two answers, probably the ones that just look really small. Well, it is the ones that look really small, which is a good thing to kind of think about. It's going to be small. All right, so the magnetic field is constant. The angle, again, it's going to be 0. So that's just going to become 1. Doesn't matter. So it's going to equal the magnetic field and the change in area over change in time. The magnetic field is 4e to the minus 6, 4 microtesla. The changing area is going to be pi times my initial, or my final area, my final radius, that's 1.5, squared. You cannot square it at the end, you have to square it inside here. Minus pi times 3 squared. You cannot pull that squared out. You can't say 1.5 minus 3 and then square that. Mathematically, these are not the same thing. So that's really the only thing you got to be careful of here. And then you divide it by 5. If you plug all that in, you should get 1.7 times 10 to the minus 5 volts. Oh, and there's a negative sign in front. Negative, negative. Again, I will purposely give you all problems where the voltage is positive every single time. The negative means something conceptually will get there. We'll get there. For now, just calculate the voltage. I don't want you all to get mixed up in that. All right, I'll give it 10 more seconds, and who knows what the delay is. But everyone should have the right, it's the last one, in case that's not obvious. All right, so we'll close it out in 5, 4, 3, 2, 1. Okay. I was watching to see if the numbers started to cascade down, and that would be my indication of how long the delay was. But, yeah, that was longer than I gave. Oh, that was the one I guess I also forgot to put. That was C. This one is D. Great. All right. Fantastic. Just some math. It doesn't say why it's changing. It just says it's doing this and this. Okay. All right. So now I get to talk about this. All right. This is very small. No one is working with 0.000017 volts. That is useless. Oh, basically useless. That is not going to make much current. For example, connect that to a 10 ohm resistor, divide that by 10, you get an even smaller thing as the current, and that's so tiny it's useless. So the question is, how do you make a lot of voltage? If only there was some way to take this number and multiply it and get a lot more of it. I want you all to think about this. Think of a circular loop of, I have a circular loop of wire. What could I do if you were designing something? If you knew a loop of wire, if I shrunk its area, whatever, what would you do to make a larger voltage? What could you do in this problem? Or what could you build? How could you design this to make it more? This is one of those rules of things. Just think of like anything in life. If you want more of it, just get more of them. So, if one loop of wire makes this, well, what if instead I had 2 loops of wire? Each of those will get this voltage. Voltage stacks. You put 2 batteries. So imagine this is a battery making this voltage. If I get another battery, another loop of wire making this, a 9-volt battery and a 9-volt battery after each other, that makes an 18-volt battery. Remember, each one's like a ski lift, raising it higher and higher. If I had 3 loops of wire, now I get 3 times this voltage. If I had 10,000 loops of wire, I get 10,000 times this voltage. So, just get a bunch of loops. However many loops you have, just multiply your voltage by it. Just put an n in front of the equation, and you're good to go. That's it. You will never find a piece of equipment that's a single loop of wire making electricity. If you ever see an electric motor, or you ever see a generator on the inside, it's just coils upon coils of copper wire. Why? In the case of making electricity, every single loop adds an additional amount of voltage. Every single extra loop that we can fit in there. And it doesn't matter how thin or thick these wires are either. They can be really thin as long as they can handle the current. The only thing preventing you from making a really thin wire is 1, is it really expensive to make a really thin wire? And 2, if I have so much current, that wire will get hot. Remember, as the wire gets thin, it gets a higher resistance. If it gets a higher resistance, it's actually just losing energy to heat, which is also not good. Wasteful. It doesn't do anything for anyone. Unless that's your goal, is to make heat. Yeah, so you put them real close. You do need to insulate these wires, because if they're not insulated, they're just going to act like one fat wire. You need to keep them separate from each other. You need them to act like independent loops. If they're not insulated, what's the difference between a bunch of uninsulated wires and just one big fat wire? Nothing. They have to be their own loops so that they each get their voltage and they add. Yeah, and that's it. Like, this is, you all know how generators work now. Like, this is, now it's just practicing it, which is cool. Just checking in up front. All right, so a 50-turn coil, which is a pretty low number. Most of these things have like 1,000 of coils. A 50-turn coil has a diameter of 15 centimeters. The coil is placed in a spatially uniform magnetic field. That just means it's the same everywhere. Fancy words for it's the same everywhere. Magnetic field of 0.5 Tesla, that is huge. That's a lot. Very hard to make a strong magnet. Permanent magnet that's strong. So that the area vector of the coil and the magnetic field are parallel. Find the magnitude of the EMF, voltage, induced in the coil if the magnetic field is reduced to 0 in 0.1 seconds. Really straightforward, nothing fancy here. I'll just kind of zip through this one. So we got N equals 50. We have the diameter equals 15 centimeters equals 0.15 meters. Let's just recognize that we're going to have to get radius. It's area of a circle. You know what? Let's recognize it later when we need it, just so it doesn't feel like I made it out of thin air. Magnetic field is initially 0.5, and it says it is reduced to 0, so that's its final. 0 Tesla, and the time is 0.10 seconds. All right, we're solving for EMF. The equation for EMF equals negative N. That's the only thing we've changed. And I'm using the calculus ones. Let's put triangles. Equals negative N. The magnetic... it's fun to write this. When you're writing this, don't feel the need, like on a test or whatever, don't feel the need to write... if you know the flux is BA cosine theta, just put that. Save yourself a little bit of time. The angle between them is parallel. How convenient. I'll be honest with y'all. If I give you a problem where I say find the magnetic flux or find the EMF generated, the angle will either be 0 or 90, but 90 would be silly. 90 would be silly because it'd be no voltage was generated, and that would just be to trick you, and that's not the point of the problem. And so just expect that cosine theta to be, if I don't give you the angle, and if I don't say solve for the angle, just assume that it's not going to matter. That's just a good kind of test-taking skill. All right, the area is a constant. The magnetic field is changing with respect to time. Put that area in front. And oh man, we need area. What's the area of a circle? Pi r squared. Oh, I guess we need that. We need radius, which is just going to be half the diameter, 0.075. All right, and then we just put it all in. Like, nothing exciting at this point, but I just want to show you the magnetic flux is 50 times bigger. 50 loops, 50 times bigger. That's the useful thing to this problem. Otherwise, it's just some math. Zero minus 5 over 0.1. All the parentheses. Oh, let's put another one for funsies. Close them all out. All right. These are great problems to go through just to make certain you're comfortable with this. They're as simple as they get. It's literally what's given, what's missing, equation, plug and chug. No algebra. no rearranging. Great starting place for doing these problems. Now, remember, this is a very strong magnetic field. Very strong magnetic field. Completely unrealistic magnetic field for a generator. But because it's such a strong magnetic field, we get a big voltage. Yeah, big magnetic field, big voltage. Now, if we had 50 less turns, divide this answer by 50. Oh, oops. Yeah, I saw some inquisitive looks, which made me think to double check it. All right, I was off by, I accidentally put 5 instead of 0.5. 50 Teslas is not existent. And I put 5 Tesla. 5 Tesla is still even more wild. All right, there we go, 4.48418. There we go. Still, this is a reasonable voltage. We can do stuff with this. And while I told you this magnetic field is huge, what I do want to point out is if you divided this answer by 50, that's what a single turn of this would do. You just divide this thing by 50, you get a really small answer. Not useful. All of a sudden, by just making 50 turns, we made it useful. Most of a generator is just copper wire wound up. They're heavy. Generators are heavy. Because it's a bunch of the whole thing's a bunch of metal as well. Your generators, all that kind of stuff. But any turbine and stuff like that, they are just chock full of metal, specifically copper. Why we use copper? Because it's cheap and a good conductor. That's basically it. Why don't we use iron? Iron rusts, and it's not as bendy. It's not as easy to bend as copper. Think of a paper clip. Well, I don't know how they make paper clips. But I'm just going to say a paper clip is just pure iron. It may be other things. A paper clip is more stiff than like a copper wire in something. So that's kind of an example of the difference between those. I'll have to actually look into composition. All right. Cool. Again, we're just sitting in this, y'all. We're just sitting in this changing flux equals voltage again and again and again and again and again. I've already kind of said this. I've given away the punchline. You rotate it. That's how things work. The flux goes up and then down and up and then down. So today, and let's see if we're going to get to the other thing. Yep. Let's see. Can we even do this problem? Yeah, we can do this one. Okay, this is a very specific case. I will be honest with you. I will not be giving you problems where the angle is changing and saying find the flux. I will not generally, this is like one exception, the only exception. And as we're solving this, I'm going to tell you why. I will not generally be giving you problems where I say find the flux due to it rotating. And the reason for that is the same reason anytime I tell you I'm not going to give you a specific type of problem. You need calculus. It always comes back to calculus, right? This just goes to show why calculus is so useful. If you ever wonder why do people have to take calculus, the amount of times I've told you all, oh, we can't do this because we don't have calculus. We can't do this because you don't have. And that's fine. You all don't need it. But it hopefully at least shows if you know someone, they're like, man, why do I have to do calculus? You can tell them. Man, my physics teacher, blah, blah, blah. Anyway. All right, so N is 1,000 turns. So a coil of 1,000 turns encloses an area of 25 centimeters squared. It is rotated in 0.01 seconds from a position where its area vector is parallel to one where its area vector is perpendicular. If the strength of the field is 6 times 10 to the minus 5, that is the strength of the Earth's magnetic field. It's very weak. What is the average EMF? That word average is the reason you don't have to do calculus for this problem. All right, so N equals 1,000. The area here is a little mean, 25 centimeters squared. And you may be like, oh, that's fine. That's just 25.25 meters squared. No, it's not. Because the centimeters is squared, you have to do the unit conversion twice. Because that centimeters is squared, you have to do the unit conversion twice. So let's just kind of write that out. So 25 centimeters squared. If I want to go to meters, I need to figure out how many. So to go from meters to centimeters, how many meters are there per centimeter? There's 0.01 meters per centimeter. All right, that gets rid of one of the centimeters. And we had so much fun doing it once. We do it again to get rid of the other centimeters. Long story short, if ever your unit, when you want to convert is squared, you have to do the unit conversion twice. It's a little mean, but it is something to be mindful of. It is something that could come up on future tests for you all and all that kind of jazz. I'll try not to be mean like this in the test. Again, I don't want you all to miss things because of stuff like this. I don't want you to miss any problem. But if you do miss a problem, it's because I want it to be because you didn't understand the physics, not because of a math thing. I want the test to test your physics knowledge, not your math knowledge. 80% physics, 20% math is my goal as far as what I'm testing you on. Anyway, the magnetic field at all times is 6 e to the minus 5 Tesla. Okay, and this is, so what's changing? My angle initially is 0. My angle finally is 90. It starts parallel. Parallel means an angle of 0. Perpendicular means an angle of 90. All right, we are solving for EMF as always. EMF equals negative. Let's just go ahead and be cool with that. These are constants, and it's the change in cosine theta over the change in time. B is a constant. The magnetic field is not changing. The Earth's magnetic field is not changing in this problem. In general, the Earth's magnetic field doesn't change. Fun fact, one day the Earth's magnetic pole will switch, and it will be awful. Due to all sorts of, because it'll cause all sorts of it'll be a changing magnetic field across the entire Earth, which will induce currents in everything across the entire. So this is a good kind of aside. Why are we so you all have heard nukes are bad. Yeah, we're all on board with that. And you may have watched, what was it, Ocean's 12, 13? I don't know. One of the things that a nuke does is it generates an electromagnetic blast. You may have heard that this electromagnetic blast in Ocean's 12 or 13 or something, they use this to shut down so this is like a common trope in a lot of things. This electromagnetic burst shuts down, breaks electronics. If you make this giant, they always use this term, electromagnetic pulse, electromagnetic burst, and it shuts down. Why? It makes a changing magnetic field. And think of all the wires that make closed loops. Your phone is chock full of closed loops of wires. If you make a magnetic field change quickly in your phone, it will make a voltage in your phone. It will make current in your phone. Your phone is not made to handle that current. It fries the wires. Your phone is toast. Anything that experiences a strong electromagnetic pulse, if it makes a strong enough voltage in it, if it's a closed loop and it's oriented the right direction at that exact moment, it makes a lot of current. That current makes heat. That heat melts the wires. That piece of equipment is toast. It's not like temporarily broken. It's broken. It's like throw it in the trash broken. Microscopic wires, you cannot repair these things. So one of the things with nuclear bombs is not actually exploding it to kill people, but exploding it in the air. It makes a really strong electromagnetic pulse and it fries everything in the area. And the entire electric infrastructure is down. And that's an absolute disaster. I mean, think of how bad it is in Florida when power goes out for like a day or two. It doesn't come back in a day or two. Every transformer, every single, everything gets blown. Entire city, every single piece of the vast majority of electrical equipment destroyed, useless. That's a lot. So anywho, now you know how electromagnetic pulses work. Another thing for you to be scared about, not nukes. I mean, if a nuke goes off, we get, like, that's a whole thing. If that happens, whatever. Solar flares. Solar flares send a bunch of, like, electromagnetic waves at us. We're going to learn that electromagnetic waves are a changing magnetic field. If a strong enough solar flare happens, it produces a strong enough if it's pointed at our Earth when it happens, it can also fry everything on the entire side of the Earth that's facing it. And there is cases of these things going off in our lifetime, like in the past years or whatever. Now, it has to be pointed right at the Earth, which, imagine firing something at the sun and hitting the Earth. Like, there's a statistically low chance of that happening, but it's possible. So another thing for y'all to worry about. Anyway, just fun asides. Why so many connections for why this is relevant? Half of them not good for you to know. I don't know. Just makes you more worried. I don't know. It's whatever. It happens. It happens. It was our time to go, I guess. I don't know. But it'll be great. Anywho, we plug in numbers. The area is 0.0025. The angle, so we can only do this change because it's average. If you actually wanted to be more rigorous with this, well, if it wasn't average, you'd have to do calculus. But it's not a calculus class, so you're spared, I'm spared, we're all spared. All right, the time, forgot to write that down, but I knew I needed it. Let's just chuck that up here. Boom. Now, thankfully, this is really simple. Cosine of 90 is 0, minus cosine of 0 is 1. So mathematically, it's quite simple. But this just goes to show you, we've done all three cases now. That's the reason I did this. We have done one where the magnetic field changes. We've done one where the area changes. We've now done one where the angle changes. We did it. This is literally the only three cases possible. I mean, I suppose you could have a combination of the two, but not you all. You all don't. Okay, and that equals a number. A very, very, very small number. This one, oh wait, I forgot my loops. I was going to say, that's so small. But don't worry, they put 1,000 loops of wire in this thing. So it's 1,000 times bigger than it would be if it was one loop. It's still very small. All right, so this is still a very small voltage. And it just goes to show you, one, Earth's magnetic field is very weak. It is technically possible for you all to power things by just going outside and spinning a loop of wire really, really quickly. That's literally all this problem is. It is possible. There is a magnetic field of the Earth. But it's very unreal. Like, look, if you want to make power, just go buy a strong magnet. The permanent magnet will last forever. Like, you can, so you all can build your own and again, every single generator you all have ever, like anything you all have ever played with. Oh gosh, y'all know those like flashlights that you can shake and it always looks suggestive? You shake it and it's got something in it and it goes up and down and up and down. I'm not going to mimic it because it's just suggestive. You shake it and there's a magnet in it. There's a coil in it. That magnet goes up and down. Oh my gosh, I made a changing magnetic field. That's how that's how those flashlights work. That's how they get charged. If you have a hand crank, you're just spinning something in a same thing. It's all every single way to produce electricity other than a battery, this is how you do it. Every single one. Okay, except for a solar panel. You're going to have to learn about semiconductors if you want to learn about those. Anyway, all right. So there you go. The calculus gets you there, but I'm not going to stress that too much. Generator. let's see, I haven't opened this. Let's see if this is worthwhile. But this is it for, like, we'll call it kind of good. After I kind of go through this, we'll call it good. This is a great stopping point. I'll do a quick recap. So this is what a generator looks like. Now, something you're noticing is that the voltage goes back and forth between positive and negative. That's because the flux, at some points, the flux is going up, negative voltage. At some point, the flux is going down, positive voltage. Remember, as it's rotating, think of these loops. Think, how am I getting more arrows? Oh, I'm getting more. Now I'm getting less arrows. So I get a positive voltage. Oh, now I'm getting more arrows. I'm getting negative voltage. What does this mean in function? It means the current goes one way, and then it goes the other way. And then it goes one way, and then it goes the other way. Current goes from high voltage to low voltage. So yeah, it's cool. If you want the current to go one way, you put a commutator on it.